Now it gives me great pleasure to introduce Eric Barron. I've known Eric since he came to NCAR as a student in the mid-1970s. He was one of the, if not the pioneer in geosciences, learning how to use general circulation models to learn more about paleoclimate. And particularly, the message I got from his work, I don't guarantee was the first time was pointed out, but anyway, that I learned that carbon dioxide was probably a very major ingredient of past paleoclimates, and that this came through Eric's work on trying to make Cretaceous climate, which is a time that was much warmer than today, and he tried to do it with everything else first, like moving the continents around and changing mountains and so on. And nothing came close other than changing atmospheric compositions. So this was about the time that I think as a community realized that changing atmospheric composition was not only a contemporary issue, but also it was a past issue in the Earth's history. Eric has, since that time, gone on and had a distinguished career at Penn State, rising through the ranks to his most notable thing he did was to set up as director of the Penn State Earth System Sciences Center, which was one of the, if not the first, interdisciplinary activity trying to bring together the different disciplines that we need to study the Earth as a system. And he, in that context, came up with very many innovative ideas to get the faculty to work together by the various kinds of carrots a manager might think of. And having done that many years and having another position in between I won't mention, he's, over the last year, upon the retirement of John Dutton, become Dean of the College of Earth and Mineral Sciences at Penn State. And he's talking today about a vision of the future in environmental research, creating environmental intelligence centers. Eric.
Thank you. So this perspective stems from about 20 years of watching the global climate, global change research program evolve. And in particular, participating in the National Assessment of Climate Impacts, where we went from this process of looking at how climate might change and then trying to determine what the impacts might be on agriculture, water, health, and ecosystems. And in the process of looking through this through time and at the national assessment, I've come to the conclusion that we're in the midst of or approaching a major transition in the way we operate and do environmental research, at least from the viewpoint of global climate change. And if I look down the road a little ways, I come to the conclusion that this is something that becomes the equivalent of an environmental intelligence center, and which obviously I'm going to define as I go along. Now, if I do my job right, my objective is for you to believe that this is a good idea and maybe is actually going to happen, but if I really do it right, perhaps you would believe that we should actually, as a community, begin to enable this process. Okay, so how am I going to do that? Well, I'm going to start with what is the overall objective that we want. And then I'm going to take a look at what I consider to be the evidence that this transition is taking place. And then I'm going to attempt to be provocative. And I'm going to take a page from the U.S. military and the description of a war room and use it as an analogy. And hopefully you won't have all sorts of negative thoughts here before you get to this analogy. If that works, and we sit there and look at what that center might look like, or centers might look like, or that approach might look, then we should ask, and it seems reasonable, then we should ask ourselves, okay, what's standing in our way? And what's standing in our way tells us what we should do next. And After getting to that point, I'm going to give an example so you might be able to imagine what the benefit will be. So that's the sequence, end product. Is this something that's actually beginning to happen, and should we even encourage it? Okay, so the objective of environmental research. From my viewpoint, it's sitting up here on the screen. It's because I look at this as it's the ability to anticipate that makes knowledge powerful. Rita Colwell, in a U.S. climate change science program effort review of the last few days, said, look, we all spend our entire lives trying to get enough information that we gain insight into the system. And our true objective in getting that insight is to try to develop foresight. And if you think about it, we have multiple objectives in doing that. One of the reasons why we want that foresight, one reason why we want to be able to anticipate, is that we'd like to protect life and property, a worthy goal. But if we can anticipate, we can also promote economic vitality. We can take advantage of that knowledge to benefit society in a whole range of activities, whether it's doing a forecast of energy needs and saving money in the process, or doing something in terms of crop prediction or characteristics that allows us to have a richer crop that feeds more people. We really want to do both of those things while simultaneously promoting environmental stewardship. And in fact, much of the Global Change Research Program, U.S. Global Change Research Program, has been focused on this notion of environmental stewardship. And I think you've just got to believe that we have to do all three of these things. It's not one or the other. Anything you do to anticipate and demonstrate what you know and what you don't know aids you in developing fundamental information about how the Earth system operates. So I see the entire objective of environmental research, of any character and flavor, that these are really what our objectives are. Now, if I'm sitting there thinking about this, and I'm purely looking at it from the viewpoint of a guy who comes out of the climate system, I see weather and climate research in service to society every time I look. I can sit there and look at weather warnings as a direct issue and direct impact, saving lives, saving money. You can look at commerce and industry and realize that many people believe that more than half of all industry and commerce in the world has some climate sensitivity to it, some weather and climate sensitivity to it. Well, we know agriculture does. We can have, just in the climate variability in this nation, over the last 30 to 50 years, we can lose 25 to 30% of a crop, just based on what the weather variability is. I know when I tried to get from Washington through Philadelphia yesterday, before coming here, that the transportation industry is highly sensitive to weather and climate information. Defense Department, ecosystems, direct tie. There's just no choice. Everywhere you look, you see where weather and climate information makes this connection. So this is what I claim. We have that four-prong approach, and what we're really talking about is environmental research as science that is in direct service to society. And that is what I view as this major transition. Whether it's because of our observing power, whether it's because of information technology, the advances in computers and predictions and climate model simulations, it's this connection to society that is driving a tremendous amount of this transition that I'm describing. Okay, that transition, in my view, stems from the fact that we can do much more. We have capabilities and abilities that we didn't have 10 years ago. And the other element, which hopefully I've already given you a sense of, is that over and over again we're demonstrating that those cases where we can combine all that information and use it to anticipate ends up to provide information that's important to decision makers, whether it's industry, commerce, agriculture, ecosystem management, you name it. Okay, so is this transition happening? From my viewpoint is there are several different signs that it is happening. This is my first one. It's what I call the expansion of the forecasting family, using forecasting somewhat loosely. And what I see is that our ability to demonstrate skill is resulting in a remarkable expansion of what we're attempting to forecast. And you all see it. Whether or not you're intimately involved in weather and climate research, you see it because we're doing air quality forecasts for cities. We're doing lightning forecasts because it's a major cause of weather-related deaths. There's forecasts for energy demand, sometimes a season in advance. We're doing UV forecasts and alerts, severe weather evacuations. We're using El Nino forecasts to decide what we plant and when we plant it, sometimes with success, sometimes not. Drought in advance. Right down to climate change to try to determine whether this will affect a bird population, a mammal population, or an amphibian population. Basically, we're seeing this steady explosion of the things that we're putting on the list that we want to predict or project because it serves society. So that's one element of this change. It's no longer a weather service that's sitting there. We're starting to add all of these different components. Okay, the second element of this transition is a change in the time and space scales of our interests. I mean, it's really something quite remarkable to realize that for a climate change problem or even weather-related commerce, that people are reaching as far back in time as they can. We're using the historical information to set up standards for setting insurance industry premiums or in order to guide the weather derivatives industry. We're going back farther in time in order to decide whether or not we can attribute the warming of the last 50 years to human activity. We know we use daily and weekly forecasts left and right, and we're watching that extend seasonal to interannual outlooks by using North Atlantic oscillations and El Ninos, and everything else is allowing people to do forecasts to tell people what to do with their roofs or whether or not they're going to have a drought season or too much rainfall in California or whether it's time to plant strawberries or something else. We have the long-term climate change where this nation is looking at its energy policy in terms of the results we get from model predictions and projections that go a century in advance. And we're getting closer and closer to local scales every time we touch these problems. So the other element of this transition is that it's expanding across time scale and it's changing its spatial scales. The other thing that you see that I think is a sign of the transition is that there's increasingly a demand for a more integrated approach to these particular problems. And part of what I just believe is the reason is because we continually see the failure of cause and effect type science. Now I can go pick on someone not in the room. Heat those potatoes too high a temperature, they cause cancer. There's somebody's correlation there. But there's so many other factors. We know that as months go by and weeks go by, we'll discover there's some other correlation and some other piece of science that's sitting in there. It doesn't work very well. We're recognizing the role of multiple stresses in every environment. And the stresses are usually land use, land cover, waste products from human activities, and climate and weather. And we need them all. You know, the example is that if you look at a decline in fishery populations in a particular lake, and you decide it's connected somehow to acid deposition, and you go in there and try to do the study and connect it to the pH with the lake. If you don't take into account the fact that upstream from the lake is increased agricultural production and nitrate runoff, and if you don't take into account the fact that around that lake, 1/3 of it is now covered by subdivisions, you can't possibly describe what's really happening to that fish population just by looking at one particular variable. Over and over again, we see that we have to look at them all, or we don't get the right answer. The other thing is, this means impacts and decisions are frequently place-based, and we have to combine this global and regional scales. I keep doubling this, don't I? Okay, another element of the transition. Increasingly, we see signs that we're willing to describe what we do in a very mature way as a service. And It becomes a service, in my view, when you recognize the failure of throwing your information over the transom and hoping somebody else picks it up and uses it in an intelligent way. I have my own personal example. I've worked for about 4 or 5 years trying to do climate simulations that cover the transition between Neanderthaler populations in Europe and modern humans, trying to explore the climate connections. A whole group of anthropologists and paleobotanists, and I'm a pet climate modeler, and I merely did my thing. I did one simulation after another and provided mean rainfall and mean precipitation, and I sat there having a beer in Cambridge with all the anthropologists. And all the anthropologists were sitting there discussing thermoregulation and the Neanderthalers because they didn't have any clothing. No buttons, no technologies, nothing. They could perhaps wrap something around themselves. This was it. They weren't hairy. How did they manage the severe winters halfway to an ice age? And so they're describing what happens in terms of thermoregulation if they happen to have an inch of fat around their fingers, because that's something that they wouldn't see preserved in the record. And they came to the conclusion that was the equivalent of a leisure suit. And all of a sudden I'm listening to this and I'm listening to this and I'm wondering how these people are surviving in the wintertime, and you all of a sudden realize they never cared about my mean precipitation maps and my average temperature maps. They wanted to know how long could that guy hang around outside the cave getting food or water before his fingers froze. That was the objective. And when we turned around and did wind chill, we discovered that the tool cultures of Europe lined up with the wind chill effect. And the more sophisticated the tool culture, the lower the wind chill that they were able to tolerate, because they were changing their clothing and their housing characteristics. This is what I call user pull. This is a case where I wasn't delivering what I wanted to deliver. I was listening to the needs of somebody else and providing it. Increasingly, we see this connection between research, operations, and decision-making. That's one example on a scientific side. But it suggests that a lot of what we do is in this service mode, and in a service mode, it's this user pull that becomes significant. Okay, my view is this is this new approach. This is what all those signs of transition are telling us. We've got to go from large scale to place-based. Otherwise, you don't connect to a decision maker. You have to look at multiple stressors. If you don't, you will always run into the case where here's the climate change, and you won't know the impact of that climate change because the other stressors are also important, and you'll never quite be able to separate them. And this notion that you put knowledge to work deliberately with this connection to decision makers. Okay. I call that the base description of an environmental intelligence center, if you could actually pull that off. It implies that you have all those data sets that are there, that you have a predictive capability, that you have an information science and technology process that allows you to deliver this information to people. And it implies this vigorous connection to users. Okay, as promised, can we steal a page from the military and the characteristics of a war room? And I stole these next couple slides directly from the Air Force Weather Service. And I looked at this, and here on the left are these intelligence sources: air surveillance, surface surveillance, space surveillance, all of this information that sounds vaguely like the weather and climate observing system to me, although it obviously isn't. And then there's this focus here, which includes all the other components of the system in terms of geospatial positioning and everything else, and the topography and geography, and it creates a common operational picture and what they call a joint battle space infosphere. This is really what we're talking about with an intelligence center, is creating this infosphere that allows someone to make decisions. And in this case, we have this very direct user pull, because there's a specific mission, and it's called the commander, who is the user pull on this entire system. Okay, and I looked at the Air Force weather mission, and it says anticipate, exploit the weather. Anticipate the weather. If you can anticipate the weather, then you can exploit the weather. That's almost like my first slide. Again, it's mission-driven, but it's almost like my first slide. Your ability to anticipate allows you to promote economic vitality, save life and property, and in our case, also do environmental stewardship. And if you read it, it's a wonderful description at the bottom of delivering information anytime, any place, highest quality, mission-tailored products and services related to terrestrial and space environment from the mud to the sun. If that doesn't sound like Earth system science, I don't know what does. That's a mild joke from someone who started in Earth System Science Center. My wife tells me I'm never funny, and clearly it's true. Okay. Now, there, a war room analogy. And now I step back and I say, we spent 3 years doing a national assessment of climate impacts. We got to the end, and what did people say was the biggest flaw? Recommendation number 1 for the future: develop a more integrated approach to examining impacts and vulnerabilities to multiple stresses. We're connecting to sectors at a regional level so you can manage and connect to decision makers. I've got to have this be an integrated approach, multiple stressors. It's exactly this description of this transition that I've been describing, right? So if that's the case, and we know what we're doing, and we know what we want, why can't we do it? What's standing in our way? Why am I standing up here talking about something where everybody looks at it and says, these are the elements that we need to do? I think this is what's standing in our way. Integration of observing systems. We do that, right? We have a global observing system, a global climate observing system, a global ocean observing system, a global terrestrial observing system. If I really wanted to be rude, I would tell you that the discussions of creating those systems would fill a room like this full of paper. And the traction in developing global observing systems is small. One of the reasons why it's small is because every time we add more elements and more observations, the size of this problem becomes larger and larger, and our ability to put our arms around the problem become more and more challenging. And I will bet anything that the Global Observing System Challenge will keep pace with climate scientists at the same rate that our demand for computer resources and to do climate modeling keeps. The carrot is always in front of us, and we're always chasing after it. And the feds will sit there and say, we heard you, you need more computer time, and they'll invest a whole lot of money. And the minute they do, they will discover that they're still way behind and getting even farther behind. And the global observing system, I put in that exact same category. We can't put our arms around the whole system. A common modeling framework that enables integrated full system prediction. I reveled in the possibilities of developing global circulation models and coupling the cryosphere to them, and coupling the hydrologic cycle to them, and coupling ecosystems to them. But again, we have this urge to go to higher spatial scales and to include all these components, and it exceeds what our capabilities are. And you can see that every time we take a leap forward, we go to higher resolution for one component of the system, and we slowly add the coupled system. It's a remarkable challenge. And we can't get down to the spatial scales that we've been describing and needing. I remember one time in one project that I was sitting there working to couple climate models to hydrologic forecast models. And at that particular time, my climate model had 2,000 points over the globe. And it took a vast amount of computer resources for that particular time. And you can imagine the spatial dimensions of 2,000 points. And I talked to my hydrologist friends, and I said, okay, what resolution do you need for us to simulate correctly the Susquehanna River Basin flow? They said about 30-meter resolution. I went, 30-meter resolution? And I did a calculation. It was 104 million points. Okay, it tells us what that challenge is to do that coupling. It's enormous. How do we do process studies? We do process studies by going the best place on the planet in order to figure out how some particular process works. We don't do process studies in a deliberate way to improve the characteristics of models or to look at a real scale set of problems in an urban or hydrologic environment. Maybe hydrologic environment we do it more. We don't do that so that we improve our predictive ability. We don't bring this discipline of forecasting to this whole process. The process studies are to learn how something happens and how it works and we have a weak connection to entraining that into our predictive capability. I'm picking on the entire discipline in this process here, aren't I? Okay. Integrated Data and Information System. If you want, you could read NASA's Earth Observing System, Data and Information System. We barely managed to handle the information and make it so that you could see what was there after an enormous amount of investment. It's the same issue. As the data sets grow and the information grows, it becomes more and more of a challenge to put our hands around it. Vigorous connection to users and decision makers, the other key element of this type of process to make this user pull occur. We barely make an investment in this if we have an operational system that we're looking at. We want to know how our users use the information, but it's a rare thing when the people that are creating the pull on the system are right there in the room at the beginning as you decide how to do things. Okay, so maybe I haven't been very nice. I do think that's what's in our way. And you can use an example if you want, and you can just sort of visualize this yourself and start to think of all the data sets that are behind there on that screen between atmosphere, ocean, terrestrial, and space-based assets. And you can start to think just for the climate model, just for the weather and climate system if you want, and look at the data coverage in 2001, and you have surface observations, and then SON data, and then aircraft measurements, and sounder data, and satellite winds, and microwave information, all that you're trying to include, and we sit there in a process by which we do our very best to assimilate each and every piece of that information into our models in order to make a prediction that incorporates as much of that information as we can. That's the task we do in making a weather forecast. We barely scratch the surface in assimilating all the satellite observations that we have coming into the system. It's a tremendous challenge to be able to do this, to do that assimilation. And we haven't touched the terrestrial part of the system. We haven't combined the hydrologic components of the system. We haven't included the demographics and all the other data about humans in this particular process. It's just telling us, as part of this objective, what a tremendous challenge it is to start at a global scale and reach a decision maker on the scale of a region. We sometimes can do it specifically with a specific mission. One of these examples happens to be the wind flow on President Bush's inauguration day, and the other happens to be a group of characteristics sitting there over the country of Iraq. And so we may be able to assimilate, fuse this information for specific purposes, but we have to recognize that we have this tremendous challenge to try to incorporate all this information in our current systems. Well, here's my argument. It's not because we're not capable. It's because we're starting at the wrong scale. The problems are regional or local. And largely our investment in exploring coupled systems, observation systems, and attempting to be holistic and putting our arms around the whole thing, largely that's been global. And we're running into this problem of not being able to put our arms around this particular system. Whereas if we did it at a regional scale first, we might actually be able to put all that information in a similar set of pages. So, this suggests that we need to look regionally. And a more realistic approach might be to attempt to put together all this data and information, coherent observing systems, process studies, predictive model components, the information technology that allows people to grab this data and work on it, the close connection with users, and do this for a region, a watershed, or a state, and have that be the focus of the effort. What I'm suggesting is that we've spent a large amount of time here discussing how we were going to do the coupled system and the integration. And the challenge is sufficient that we have to hit this problem from more than one direction. And one of those directions we have to do is to start at the scale of the problems and work at promoting that integration. And I think if you're successful, what I would claim is that you will create information envy like nobody's business. And the level of user pull that will occur will mean that you will go from single regions for which it's obvious for all that data sets to be sitting there easily accessible, and all the data sets being in a coherent framework, and even observation systems, so that instead of having 14 different agencies responsible for different sets of information, you have a coherent structure, because it's easier to do at that scale than it is to do nationally or globally. I think you'll create the information envy, and the pull on that information, and the pull on those model predictions, that we will end up creating a national scale system and a global scale system in the process. You know, and I got to tell you, I don't want to reverse what's going on at a global scale. I'm just saying we need one more approach to add to this particular process. If you did that, if you put together all this structure and information, my bet is the same structure and information would hit all of these problems. It is the same information, the same weather observing system that we use for all of these different processes and predictions and forecasts. All of the same information. Put it together in an accessible way. Work on building the model structure and prediction at a mesoscale that allows you to couple ecosystems and water and human health. I think you'll hit all of these. I highlighted one, human health, just to take as an example. Suppose our target, we needed a target for initial success, and we decide we're going to do a Northeast Regional Health Alliance. No, purely accidental that I picked a region that happens to be where I come from. Okay? And the whole idea here is to develop this integrated framework with the objective of coupling environmental health with a mission which is to limit adverse health outcomes. Why did I pick that one? One reason why I picked it is because the health community rarely anticipates anything. Occasionally we do it for something like flu virus, but largely the health community is a point-of-service community. When people start coming in the door and they're sick, that's when people go into action. When something expands to too great a level, that's when the investment in vaccines or other characteristics takes place. And we don't usually do this in an anticipatory mode. If, in fact, many different health characteristics, and I don't care whether it's heat stress or whether it's pollution related to respiratory problems or whether it's vectors that are delivering infectious diseases, if those things are coupled to environmental factors and those environmental factors have a level of predictability, then we can move to the point where there's real potential for identifying adverse health outcomes in advance and limiting them and being able to address them. And it's also obviously a visible and important problem to the nation. The benefits are on multiple timescales. Historical timescales, I get to define processes and relationships. Current weather, climate, environmental information often can tell us exactly what's going on right now and decide how it is that you're going to mitigate adverse health outcome. Seasonal to interannual allows you to apply resource allocations or have a warning of a disease in advance. Decades to centuries allows us to do a better job on the U.S. national assessment of health impacts associated with climate. And I'd just like to point out that the health assessment was viewed as one of the weaker in terms of coming up with robust conclusions on how climate would influence human health. And the reason was a stated inability to combine climate, landscape, the biology, human behavior, and then link it to what was going to come in the door at the doctor's office. That's exactly what we're talking about. Okay. There's clearly associated disease with multiple stresses. Weather and climate, land cover change, pollutants. And I don't care what you look at. You can make a list much longer than that. The distribution and timing of vectors that deliver infectious diseases is absolutely connected to weather and climate conditions. Mosquitoes can overwinter and be a reservoir of a disease like West Nile virus, and that completely changes the dynamics of the next year. Incubation periods of diseases are often coupled to temperature. The availability of hosts or food availability for hosts often is defined both by climate and landscape characteristic, as well as pollutants. The contact with human populations, the same thing, often has a tight correlation with what the landscape is like and what the climate is like. And it goes on and on and on. In order to solve that problem and really anticipate adverse health outcomes, you have to address multiple stressors at a spatial scale that suits this particular problem. Okay, could we take two examples? West Nile virus, Lyme disease. So here is West Nile virus surveillance in the state of Pennsylvania at the end of a season. Not this season, the year before. Red shows where the virus is present. It's a dead crow, a human case, human death, horse infection. About a third of the horses that are infected die. I think for West Nile we lost about 12,000 horses or something last year. It's a significant disease. Now, there it shows the distribution of the virus. And just so you know, enhanced surveillance occurs anytime the county next door has had a confirmed case. That's the extent of the advanced warning system for a virus that people care about. But you start to think about all these observing systems and information and how that might blend together. And you all of a sudden realize that if we use our weather radars and do precipitation and NASA develops a soil moisture indicator, you can actually determine in advance whether the water is ponding or not and make the decision to use a benign larvicide that kills the mosquitoes before they hatch, or whether you're going to risk it and allow them to hatch out and have to use a much less benign aerial spray. That's one example. West Nile virus is coupled with bird population and a mosquito population that if you have an increased tendency towards drought and the birds congregate at particular water holes, all of a sudden you develop a very fast reservoir. And if you follow that drought period by a period of enhanced rainfall, you get an explosion of West Nile. So this suggests that any ability we have to anticipate climate on a 3-month, 4-month, 6-month year in advance would allow us to do focused studies on West Nile that would tell people what was happening far in advance. There's scientific questions that are embedded in this. Why the distribution of red counties? Are we watching the case where the in-between counties have West Nile virus and we just haven't identified them? And that what we're looking at is how West Nile diffuses across the landscape as we begin to warm up in the summer and the mosquito population spreads from the coastal areas into the interior? Is that what's going on? Or are the birds, coupled with land use and land cover, hopping across the landscape because of distribution of things like corn that they're feeding on? And so we're setting it off in a particular pattern. So we end up having this infosphere that you develop have immediate impact, season advance impact, greater understanding of what the processes are like, and I'm willing to bet that if you do a really good job, the next time you do an assessment of climate impacts or global warming, you'll have a much better idea of what West Nile will be doing than you do today, for which there's no environmental information that allows you to anticipate and predict. And instead, we do surveillance of where the dead crows are. Okay. Lyme disease is another case. Lyme disease is also a serious disease in the U.S. That's what the distribution of cases with risk analysis that's occurring. Now this time it's delivered by a tick. And the tick has feeding populations that are mice and deer. And again, if you start to imagine here how deer populations, mice populations are governed by land cover change and by climate, there is the potential that you could actually anticipate the distribution of Lyme disease. Already we're discovering that how Lyme disease is spreading in Illinois is spreading based on particular vegetation patterns, and the particular vegetation patterns are correlated with soils. You would never do that. You would never know that that was occurring without starting to develop this infosphere. Okay, and just to give you an idea of the climate connection, this is a county in Pennsylvania, 1-year lag, the number of days that have 50 to 60 degree temperatures in fall. And there's really a good correlation between Lyme disease and the characteristics of fall temperatures the preceding year. Information like this, because you're directly trying to put your hands on this information that combine the health community and the climate community, could allow you to provide Lyme disease alerts for particular seasons of the year 1 year in advance. That allows you to anticipate an adverse health outcome and do something about it. Okay, you're getting tired of me? This is what I'm asking you to imagine before I spin around to the point where I trip. Imagine if we could develop a system where we could really develop this cohesive observational framework and put all of these observations at people's fingertips with a data and management access system that basically ensures that all of this, co-located, independent of what organization, this is the scale, a regional scale or a state scale, is a scale at which we could actually pull that off. Develop a framework for developing regional predictive models. I would propose that what we're doing in advances in mesoscale modeling and atmospheric science provides the perfect foundation for that coupling, to add in the ecosystem dynamics, to add in the hydrology, and to begin to work truly on an integrated coupled system models at the scale that's appropriate for the problems we deal with. If you had that framework and the modeling to begin to hang this information on and the match with all of the observational information, all of a sudden you direct process studies. Because now what we're doing is we're bringing the discipline of forecasting to a wide range of environmental problems. Not just looking for correlations of cause and effect, but using those models and the observations to make a prediction, and when you fail, to discover why it is that you fail and what needs to be done to improve. This is truly bringing the discipline of what is a foundation in weather forecasting to a broader range of problems. And now, as you connect with health, or water resources, or water quality, you can begin to think of this vigorous connection with the users that you can't do on a global climate modeling basis. Because nobody cares about the globally average surface temperature. Or you can look at global energy policy, but you can't truly look at health, water, food, fiber, the things that people really care about. Okay, it isn't a war room. So I gave the analogy because I like this notion of an infosphere. I like this notion of being pulled on by particular missions and tasks. But we really have all of these objectives in mind: limiting threats to life and property, enhancing economic vitality, enhancing our ability to be environmental stewards, and learning the next thing so that our insight grows and our ability to derive foresight grows right along with it. So there's our objective. Bring the discipline of forecasting to a wide variety of environmental problems. And you do that by creating a powerful data and information system tightly coupled with a predictive capability that also has a vigorous connection with decision makers. Okay. That's what I call an environmental intelligence center. And my belief is this is exactly the direction we're going. And we're doing it in an interesting way at a global scale in which we're trying to add more and more observations to our global observing system, and unfortunately creating more and more paper as we go along, as trying to make global climate models more and more sophisticated, and trying to scale down to the point where we connect with users. But what we've lost is a real ability and focus of integrating systems and have that close connection with decision makers. And I think we're seeing this natural tendency from the national assessment and all sorts of other different agency efforts and ecosystem description efforts to get closer to that region and coupled system. And the only thing that I'm suggesting is perhaps it's time to do this deliberately. Perhaps we should deliberately be picking particular regions and particular problems where the entire objective is to put that information together, have an information and science technology process that makes that information accessible to a wide range of people, deliberately pick a modeling framework at a scale that allows you to begin to hang on different couple components of the system. Bring the discipline of forecasting through that process by all of a sudden having directed process studies towards enabling forecasting and prediction or projection as opposed to crossing the world to get the best understanding of a particular process. Bring in that vigorous connection with users right from the beginning. I think that it might turn out to create a world in which we develop this tremendous information envy. And we watch something like this grow when people realize what the potential is to connect with things like health, water, and agriculture. Thank you very much for your attention. Do you want me to? Right.
And I guess the Western Islands just have one good one. That's the way out there. We're islands.
Right.
Clearly,
Right. They certainly are. And of course, we busily do mesoscale weather forecasting for regions, and we either define the boundaries with observations, or we can define them with other larger scale models. Or people also do all sorts of levels of downscaling, and none of them may be perfect, but part of our objective is to learn how to do this integration. So I think we just have to take advantage of the fact that there are many different styles and ways that people are connecting the global weather and climate system to regional systems. Mesoscale modeling is a perfectly good example of that, and how we set up mesoscale model experiments. So we will have boundary condition issues, but I don't think they'll stop us from doing this. Yeah? Yeah. Yeah, I'm actually not planning to get around them. I'm planning to enjoy them. Because I really think this is, this would be similar to what you would look at if you went back in the 50s and started to describe the whole process of learning how to forecast the weather. Because the problems were vast and many. And then you spent the next 50 years going through this discipline of forecasting, predicting, failing, going back, doing the studies, adding to it, and increasing the capability. And that is exactly what I'm talking about. And I'm basically saying these connections to society are so important. Let's begin that discipline of forecasting environmental factors and importance to society. Let's start early. Let's start to do it deliberately. You may not make decisions on a lot of these things for a very long period of time, because you have to go through this whole evolution of beating back a lot of these problems. But I already see, if I could actually tell the state it's going to be a bad Lyme disease season, do you realize that spring and fall temperatures are bringing people into the woods if they're warm enough, and then that's the same time you're also hitting the activity levels on these diseases, and this is the reason why you have this explosion of cases? It's just too nice a thing to be able to warn people in advance. So, yeah, there'll be problems, but it'll be fun to beat them back. Yeah?
As scientists, we appreciate the interest of doing this sort of thing. We also appreciate what you're saying about the user pull being important. To set up projects of this nature, you pull from the users to a certain sense, and obtain resources to set up the research efforts. My question is, how do you tell users who may not yet know that they need this information, that they should keep working?
Yeah, it's really a combination. I firmly believe that part of the task is putting people in the room together that have common interests. And just like that Neanderthal climate connection there, it starts to happen and you realize you're playing a different role than you used to. And I think already the health community, you can watch how it is that they're approaching West Nile and how it is they're identifying cases and what they're desperate to know in order to do mitigation or to have some sense of what the next season will be. And you realize that you can actually make a big difference in providing that data. It's not there for them. The notion of going out into the atmospheric community and picking up information about precipitation in some way in which you're doing summaries over a 3-day average or 4-day average of the incubation time for mosquitoes is outside of their range. So I think you take specific examples. That's why I tried to go health, and then to a specific example. Start to prove the concept and start adding to it. That's my, it's the opportunity to start to prove that it works. A lot of it's happening anyway. I just think we should be deliberate about it. You want me to take one more or not? Yeah. Yeah.
What is your opinion? How do we need to change our communication program
Yeah, it's a challenge, but well, the question is basically, can you define educational systems that would help promote the solution of this particular problem? And I think there's a lot of innovative ways in which people can do teaming of different disciplines by the time they hit a graduate level that would really enable this to occur. But I agree, that's a challenge, especially with modern universities. That's a question you should ask a dean sometime. Okay.
Okay, look, let's stop now and give Eric another round of applause.